it had many problems. And actually, I have really stated which are the problems. And the main ones are the fact that in 1800, when he performed the experiment approximately, he thought that by taking spherical metal iron balls and placing them close to a torsion balance, he would have actually measured the actual force of gravity in terms of neutral attraction between masses. But the point is that if you actually consider the actual conformation and configuration of metal, you would know as a chemist or a chemical physics or somebody which is close to studying the structure of matter, that metals are of course neutral in the inside when they are placed to earth, okay, when they're grounded. But if you consider very well the surface of metal, then you would know that the metal oxidizes due to the interaction with atmosphere, and moreover, once you get to actually oxidize the metal, you have absorption of many substances, many chemicals on the surface. So this actually presents many issues on how you measure the gravitational constant through the torsion balance experiment, but also through other interferometric measurements, such as cold atoms Raman interferometry. Because in any case, when you actually measure something through metals, you have to take into account that the surface, being oxidized, actually chemisorbs many substances like CO2, water, and also other agents which might stick to the surface of metals. These metals reactions produce what we call surface potentials, patch potentials, and patch potentials are actually very strongly indicating that the force between metal balls like Cavendish was using in 1800 may perform the same amount of force as he actually figure out as being the gravitational constant. So the next question is, I find it imprecise because the stationary mass and any disturbance can cause this shift. Well, you can say that it was imprecise. Allora, l'amico inglese sta dicendo è stato impreciso perché se si muove la massa stazionaria può generare dei disturbi a causa del cambiamento. Good evening, Gaetano. We are performing an English-Italian live tonight because I have received some questions in English, so I'm trying to answer in English and then translate in Italian for those of you which have problems in actually understanding the whole of the problem. Now, the point is that you don't really have this. Okay, the Cavendish experiment might have this sort of issue that this English friend is assessing. So if you place a stationary mass close to a torsion balance, you might have some displacement which is not being controlled. Okay, if I perceive well, Mr. Flatpone, okay, so Dr. Flatpone and whatever, I'm sorry if I pronunciated wrong your name, for example, by occasionally shifting the masses or producing some thermal convection forces which produce quite strong forces, or for example the simple Einsteinian photoelectric effect, which has to be taken into account when you try to measure such a small constant like the gravitational constant. So there are several effects that have to be taken into account in order to establish a good measurement of this very small constant, which is extremely important, not only in the galactic environment, but throughout all the anthropic principles, which consider the gravitational constant as being fundamental for the building up of the universe, but not only in terms of galactic proportions, up to the formation of molecular organisms capable of reproducing life. If you follow Stephen Hawking in its Grand Design book, you can really perceive the importance of the gravitational constant, not only in the formation of the universe, which of course is crucial, but throughout the formation of any sort of living organisms and species throughout the gravitational constant. Quindi chiaramente diventa più complicato. Grounding doesn't really do anything. Induction happen everywhere. That's why I dislike those tests. Well, that's the point. Our English friend is getting very close to the aim. I don't know whether you have followed my life, but I have presented a scientific article to Springer Nature in which I point out that grounding it's not really that doesn't do anything. It does a lot in terms of shielding most of the electric charge being present on a metal, but the point is that you don't only have charge inside a conductor, but you have many issues on the surface of a conductor, which are often considered minor issues by physicists, but instead those that study chemistry and chemical physics and structure of matter know very well that the surface of a metal has various problems that have to be solved in order to be very precise in measuring anything you want to be related to the real substance, which is the metal. Okay, because the surface of a metal is not at all a metal. The surface is oxidized, always oxidized, okay? Just think of planes which have aluminium. They always have oxidized aluminium. Otherwise, the aluminium would react with air and then it would be actually well, aluminium, like all metals, is very reactive towards air. And the problem is that if you do not have oxidation, you get rust. You know, for example, if you have iron reacts with air, but doesn't really oxidize only. If you have iron, then you have oxidizing iron, but also hydroxide irons, and that is rust. And if you start rusting an object, then it creates huge problems in terms of the structure of the metal, but also its force, its being capable of doing its job at various levels. That is why we often use steel instead of iron, because iron reacting with carbon makes steel, and steel gets oxidized but doesn't get rust, and that is very important, for example, for the possibility of using material without losing its consistency. So the point is that metals can be used and are certainly the ones which are mostly indicated for performing experiments, also in the metric environment where we want to, for example, measure the gravitational constant. But we have to be sure that on the surface of the metal we do not have other substances, and this is performed very well in for example, the field which I come from, which is atomic dynamics, molecular dynamics, and also structure of matter, because every time we deal with metals, we often use spattering, annealing, and also backing up, which are certain procedures which produce a very important purification of the metal. So by using these methods, we remove the chemicals which are on the surface and then we are sure that we are treating a pure metal. Otherwise, we have these patch potentials which I've simulated and which perform exactly the same force as that one which was measured by Cavendish in 1800. I don't know whether I was sufficiently clear in explaining why we have to treat metals with extreme caution, because otherwise we risk to consider the metal in terms of pure metal even at the surface, which is not true. Ok, so that is very important. Ok, la situazione di stallo. Thanks. One last thing. What about polarity? It only takes a fraction of a second to disturb it. Well, polarity is something connected to the amount of charge present on an object. Okay, if we consider polarity as a simple plus or minus field present on a surface, for example. Well, this depends very much on the amount of charge which is distributed on the surface. This is, of course, connected to the Gaussian theorem. Okay, Teorema di Gauss theorem. I don't know whether you are expert of physics, but for example, we know that the charge being on the surface is of course connected to the amount of charge being present on the overall surface, being integrated over the whole surface, and that is, okay, Simon, very welcome. We are treating in English tonight's live because I have perceived a number of questions in English, and therefore we are mixing up a little bit of Italian and English, and therefore we are trying to make the live being readable or audible from both parties, okay, from Italian and English speaking people. So the point is that polarity is very much affected by the amount of charge being distributed on the surface. And nanocharges, because we're talking about very, very small charges on the surface as a whole, because it's very easy to shield charges, but when they are so small and depositing on the surface of a metal object, for example, then it's very hard to control them. And we know that, for example, very small dust particles hold as much as nanocharges of electric charge. And when these particles actually absorb or chemisorb on a surface, then they might change polarity because of the Gauss theorem, which is saying, of course, that the whole of the charge integrated over the whole surface is actually determining the polarization or the net charge being present on the surface as a whole. So it's very much true what you're stating, that the fraction of a second can really disturb the amount of charge being present on the surface of a metal, but this of course is also a problem in the torsion balance experiment, because any charge can deposit also on the torsion balance spherical masses, as well as on the spherical masses which are set on the surface close to the torsion balance. So even when you perform an experiment such as the torsion balance experiment performed by Cavendish, but still being performed, you have to be very careful in shielding the overall system from these kind of problems. So I think that is pretty much sensible. I don't know whether I've been sufficiently clear in explaining what's happening.